Welcome, and today we're going to be talking about how to linearize graphs in AP Physics C. So the very first thing we need to talk about is what is linearization? And ultimately what we're trying to do is take a curving graph and make it a straight line. And it's not easy to take something that's supposed to be curved or bent and make it straight, or make something that is straight, curving or bent. They're not supposed to be that. I mean, look at this guy here. Like he's trying to make this a straight bar bent, and he's strong and terrifying looking, and even he's struggling with it. So this is not an easy task to do. It is essential, though, in the lab-based FRQ, which we know is the free response question number 3 on the AP Physics C exam. In order to be able to solve those questions, this is an essential skill that we have to apply to those FRQs. So formal definition that we could think of is the process of changing what we're plotting on the axes of the graph, and then modifying the data as such so that the result of our data that we're graphing goes from being what would be nonlinear to being linear. So why do we need to do this? Obviously, if we have a data set that's a nonlinear relationship or is not going to give us a straight line when graphed, then we want to be able to plot something different with that data to create a linear trend line where we can get slope, because the key is getting slope. Let's look at an example, and it should make more sense. So we're given some data here. There's like a x-axis and y-axis here. These are commonly called t-charts, or independent dependent variables. Now, if we just graph x versus t, then we're actually going to end up getting a parabola. Let's go ahead and try that. And you can see here, once I plotted all these points, that it is in fact that parabola. So there's an interesting thing that we can do with these nonlinear data sets like this. This one's a quadratic. We can change what we're plotting on the x and y axis, and we can actually make it appear to have a straight line. So what we can do, for example, here, let's just go ahead and plot, instead of time, t, and x for position, let's graph time squared on the x-axis and position x on the y-axis like it says here. So let's go graph this data set. Now this is the same data set. If you notice down here it says the source data, meaning the original data set that was collected, is being used in both graphs. We're just going to take the time values of 1, 3, 4, and 6, and we're going to square all those 4 values. So it's 3 squared is 9, 4 squared is 16, and 6 squared is 36. And we're going to plot that on the x-axis instead. So if we do that, let's see what happens. And look at that, we get a linear trend line. So we did, in fact, make this curve into a straight line by modifying our data set, meaning squaring all the values in this case, and plotting then the square of those time values on the x-axis instead of the time values alone. So once we have this, like, why are we doing this? Again, is we're trying to use this linear graph of the same data set that we had that was supposed to be curving so that we can get the slope. When doing a regression, you would need a computer to get the parabola's quadratic equation for this. So we can't do that with graph paper by hand. So what we're going to do is a little sneaky way to do this, which is going to be to graph then this x versus t squared, get a straight line, and then that slope is essentially going to be something we can get easily, and that's going to be a way of doing a regression on a nonlinear curve. Okay, so let's get over that stuff. What are we going to do with this? Now that we have a straight line graph, like we said, we can easily get the slope, and so we're going to use that slope to calculate unknown information about that experiment that we did. One thing that we can do just to make things easier is I can look at the x and y points and choose 2 points on the line. I don't want to use the data points ever, but I can choose any 2 points where I can easily get coordinate points and then use like rise or run to try and get the slope. That usually causes some issues with students because they're trying to estimate like what 2 points to use, or they accidentally use a data point when they're not allowed to. What's easier to do is just to take the data set that you have and just type these values into Desmos. So I'm going to go up here and I'm going to grab these values. I'm going to cut and I'm going to go over to Desmos and I'm going to paste them in. And you can see it just cuts and pastes right in there. I can then zoom in on the data if I needed to, and then I can run a regression right here. You can see here that my slope is going to be 2. So now I can jump back over to our graph and I know that the slope is 2. So those are the 2 ways you can get slope by hand or using Desmos. I would encourage you or prefer you to use Desmos because it's more exact and it's less error prone than doing it by hand. All right, so when do we need to linearize graphs? We talked about what linearization is. We talked about why we need to do it. So when do we need to do this? Like when is this going to bubble up in AP Physics C? Again, those lab-based FRQs. This is FRQ number 3 of the 4 FRQs that are on the exam. Number 3 is always going to be a lab-based question where you have to do linearization. So ultimately, when we need to do this is if you're given a set of data that's in a table and it's wanting you to figure out what needs to be plotted to produce a straight line graph. So more broadly, why we're doing this again was to create a straight line relationship when we had 2 variables that are related in a nonlinear way. So that's ultimately the goal, is to create a linearized graph so that we can get slope from that linearized graph and use it to calculate the value of an unknown quantity. Okay, so let's look at how we do this. So we talked about what it is, we talked about why we need to do it, and when we're going to see this. So how do we go about doing this? These are 3 major phases or steps that we're going to be doing. We need to identify the underlying equation for the data set that we have and the situation or context that we're dealing with in the experiment or problem. We want to then determine with that underlying equation what axes we need to have on our graph in order to have a linearized graph. This also includes figuring out what the significance of the slope is, meaning if I get like the slope to be a number like 5, what is 5 equal to? What's the significance of the slope? How does it allow me to calculate an unknown variable? And that's what we're going to do in number 3, is to use the slope number value or numerical value for the slope to then solve for an unknown constant. Okay, so I'm going to explain these quickly and then let's get to an example. So the first step we talked about is identifying an underlying equation. So this is not as tricky as it sounds. Really, we just treat the variables in the table that you have. Like in our previous example, it was position x and time t. Treat them as givens. You know, if the problem said, hey, you know the position x and the time t, you know, so those are going to be variables we need to have in our equation, as well as anything that is unknown that we're going to be asked to solve for or that we're holding constant in the experiment. This is just like we would do with any other physics problem, like word problem, FRQ, etc. Okay, and so once we have that underlying equation, that's going to allow us to determine the axes that we need for our linearized graph. And as it says here, you know, any good experiment, we're going to have an independent variable. That would be typically what's on the x-axis. That would be values that you're choosing to test. And then you're going to measure the effects of your choice for different values on a dependent variable, which is typically the one that's plotted on the y, trying to see if the dependent variable is affected by different values of whatever's on the x-axis. And then you're holding everything else constant. So that means that what we're going to do is we're going to lump all of our constants together, and that's going to end up being our slope when we figure out what the value is. So we need to figure out how to modify the x-axis and y-axis, or in particular, the values that we're going to be plotting, for example, position x and time t, in order to create a linearized graph. In the previous example, we had to square those time values, right? And the underlying equation is going to tell us how to modify the data. It's going to tell us that we need to like square the time or square root the x or whatever it needs to do. And remember, this underlying equation is going to have those independent variable and dependent variables in the equation, and then everything else should be known constants or the one unknown that we're going to ultimately be solving for. So in order to figure this out, what we're going to do is we're going to lump all of the constants together and have them be one side of the equation. And that's going to be our slope. The other side then is going to end up being some independent and dependent ratio that we would have equal to slope, right? So that's going to be your y-axis over your x-axis is the slope. So once we lump all those constants together that are going to make up our slope, they should be equal to then whatever we want on our y-axis and whatever we need to have then on our x-axis. And that's going to be how we can then create a linear shape. And again, once we know once we plot the graph, then we can go ahead and get that slope value and use it to calculate an unknown constant. Let's try an example. So we're going to go back to the same example that we did before. And this one, it's saying the context is that the position of an object that's moving with a constant acceleration is shown at different times in the table below. And it's saying that it's starting from rest, so it's starting with a speed of 0 at a position of 0. So the underlying equation here is going to have to be something that has x and t. It's going to start from rest, so that means that v naught is 0. And so this is a great equation that we have here that fits this. Notice also that constant acceleration is in this, so v naught is 0 in this case because it's starting from rest, and x naught is 0 in this case because it's starting from x equals 0. So that means that this underlying equation actually reduces to the one you see here. Now in the problem you can see now it's saying indicate what quantities we want to graph on the horizontal and vertical axes that would produce that straight line. So this is going to jump over to our second step of determine what we need to have on our axes to produce a straight line. So what I need to do is take my underlying equation, I got to lump all the constants on one side. So 1/2 is a constant, a is a constant, and remember x and t are the independent and dependent variables. So those aren't constants. Those have a bunch of different sets, an actual set of values that they have, right? So I'm going to focus in on just isolating all the constants, the 1/2 and the a. And to do that, I just got to divide both sides by t squared, so that now my right side is that 1/2 a. It's all the constants lumped together. When I do that, I notice then the other side is going to end up being the rise over run. That's going to tell me what I need on my y-axis and what I need on my x-axis. In this case, it's going to be x over t squared. So my y-axis is going to have to be x, and my x-axis is going to have to be t squared. And that's what I have right here. So again, the y-axis is going to be our position x, the x-axis is going to be time squared, and that means our slope, whatever value we get for that, I can set equal to 1/2 the acceleration, and ultimately then solve for a value for acceleration from our data set. Okay, so I'm going to go ahead and just start to solve this problem now that we've kind of talked enough about it. So again, it's saying indicate what quantities could be graphed to yield a straight line that could be used to determine a value for acceleration. So I'm going to plot my horizontal axis, the time squared values, and then the vertical axis, the position x. So it says then to, in the table below, record any quantities you indicated that need to be plotted that are not already provided in the table. Loaded sentence, but what that means is I need time squared values, so those weren't originally provided, and I indicated that I needed them here. So I'm going to go ahead and then record those values in the empty space here. It says to label the column and include units, so I did t squared, which has units of seconds squared, and I just went and calculated all these by hand. Now it's saying on the grid below, we want to plot those data points that we have here for the quantities indicated in this part. And we're going to clearly scale and label all the axes, including units. And we're going to draw the line of best fit that represents the data, which I know is going to be linear based on my plotting x versus t squared. Okay, so I went ahead and I just plotted these on here for you. So I scaled this out. We've already done this one. We did this in the previous example. So now I'm going to go ahead and focus in on the fact that decimals, remember, gave me 2. So since that's the value of the slope, and I know from this equation that the slope is equal to 1/2 the acceleration, then I can set the number value for slope to equal to 1/2 the acceleration and solve for acceleration. And that allows me then to get the acceleration to be 4, and that is a way I can determine an experimental value for acceleration using an entire data set without having to do computer regressions and curve fits like quadratic curve fits and that sort of thing. All right, thanks everyone.